Water clusters are small, temporary groupings of water molecules that come together due to hydrogen bonding. These clusters can contain a few molecules or up to hundreds of molecules, and are constantly forming and breaking apart in liquid water. The structure and stability of water clusters can vary depending on factors such as temperature, pressure, and the presence of other substances. The study of water clusters is important for understanding the properties and behavior of water, as well as for applications in fields such as chemistry, biology, and environmental science. In chemistry, a water cluster is a discrete hydrogen-bonded assembly or cluster of molecules of water. Many such clusters have been predicted by theoretical models in silico, and some have been detected experimentally in various contexts such as ice, bulk liquid water, in the gas phase, in dilute mixtures with non-polar solvents, and as water of hydration in crystal lattices. The simplest example is the water dimer, H2O2. Water clusters have been proposed as an explanation for some anomalous properties of liquid water, such as its unusual variation of density with temperature. Water clusters are also implicated in the stabilization of certain supramolecular structures. They are expected to play a role also in the hydration of molecules and ions dissolved in water. Clusters, as configurations of water molecules whose total energy is a local minimum. Of particular interest are the cyclic clusters, H2O, N. These have been predicted to exist for n equals 3 to 60. Research shows experimental result of the size of water cluster with 20 water molecules of 0.822 nanometers. Research uses of graph invariants for efficiently generating hydrogen bond topologies and predicting physical properties of water clusters and ice. The utility of graph invariants is confirmed by considering two water clusters, the H2O 6-cage and H2O 20 dodecahedron, which associated with roughly the same oxygen atom arrangements in solid and liquid phases of water. At low temperatures, nearly 50% of water molecules are included in clusters. 13. With increasing cluster size, the oxygen-to-oxygen distance is found to decrease, which is attributed to so-called cooperative many-body interactions. Due to a change in charge distribution, the H acceptor molecule becomes a better H donor molecule with each expansion of the water assembly. Many isomeric forms seem to exist for the hexamer H2O 6, from ring, book, bag, cage, to prism shape with nearly identical energy. Two cage-like isomers exist for heptamers, H2O 7, and octamers, H2O 8, are found either cyclic or in the shape of a cube. Other theoretical studies predict clusters with more complex three-dimensional structures. Examples include the fullerene-like cluster, H2O 28, named the water buckyball, and the 280 water molecule monster icosahedral network, with each water molecule coordinate to 4 others. The latter, which is 3 nanometers in diameter, consists of nested icosahedral shells with 280 and 100 molecules. There is also an augmented version with another shell of 320 molecules. There is increased stability with the addition of each shell. There are theoretical models of water clusters of more than 700 water molecules, but they have not been observed experimentally. Several models attempt to account for the bulk properties of water by assuming that they are dominated by cluster formation within the liquid. According to the quantum cluster equilibrium QCE theory of liquids, n equals 8 clusters dominate the liquid water bulk phase, followed by n equals 5 and n equals 6 clusters. Near the triple point, the presence of an n equals 24 cluster is invoked.
In another model, bulk water is built up from a mixture of hexamer and pentamer rings containing cavities capable of enclosing small solutes. In yet another model, an equilibrium exists between a cubic water octamer and 2 cyclic tetramers. 34, however, no model yet has reproduced the experimentally observed density maximum of water as a function of temperature. Water clusters play a role in processes such as solvation, where molecules are surrounded by water clusters, and nucleation, where clusters form the basis of new crystals. They also play a role in the unique properties of water, such as its high heat capacity and surface tension. Researchers use techniques such as spectroscopy and computer modeling to study water clusters and their interactions. Water clusters are not only of scientific interest, but also have practical implications. Understanding their formation and behavior can lead to advancements in areas such as materials science, drug delivery, and environmental remediation. By studying water clusters, scientists are gaining a deeper understanding of one of the most essential substances on Earth,